Hello everyone, we are Team D6, and our project is EyeHear, a vision audio fusion system for multi-person captioning. First, I'll explain our use case. EyeHear is an integrated software, hardware, and signal processing system that captions a video with separate captions for each speaker, as you can see in this example image on the right. This allows viewers to clearly see what each person is saying, and lets them focus on what the main speaker is saying at any given time. There are multiple applications for a system like this, from broadcasting an improv experience to transcribing a conversation between friends. Common captioning software only generates one set of captions, which can be confusing to read if there are multiple speakers. One solution for this is to give each speaker their own mic to speak into, but this can make the system trickier to set up and to use. EyeHear offers a more user-friendly interface where users can simply sit in front of the device, start the recording, and talk. This setup also makes the system mask-friendly, which is becoming more important now. Now I'll explain our use case requirements for this project. One of the most important requirements of our system is that it be able to generate accurate captions. We measure this accuracy with word error rate. Our aim for this project has been to get a word error rate of under 20%, which is the Microsoft standard. And the results for this metric will be discussed later, but we did achieve that less than 20% word error rate. Now, because this is a multi-person captioning system, we want it to work with at least 2 people, which it does. And we also want to provide a high-definition experience for users, which means at least 720p resolution. That's the definition for minimum of HD, which we confirmed with our camera specs. And we also confirmed we can get 30 frames per second. We also need our system to be able to sample audio between 20 Hz and 4 kHz, which is based on the range of human voice, which we confirmed we can do through our mic specs. Finally, we want our system to be portable and to fit on an average-sized conference table. We didn't end up weighing our device, but it does fit easily on a conference table, and it's light enough for us to carry around, and you'll see images of the setup later on.
So, here's the hardware setup that we have. You can see the audio interface in front, and the Jetson TX2 developer kit on the cardboard box. For our camera, we used the CSI camera that came with the developer kit. It's a pretty high quality camera, though we only use the 720p 30 fps output for our project. And here's the audio interface. We use the 2 XLR inputs on the front to connect to our 2 microphones. And these are the Rode M5 condenser microphones that we're using. They have a cardioid pickup pattern and overall sound pretty high quality relative to the other microphone arrays that we tried. Alright, so here's our setup, and this is the website. And yeah, you can start the recording by hitting this button. And you can see all the processing here.
Hi Larry, I'm currently trying to get the system working. 1, 2, 3, elephant, kangaroo.
And you can see Charlie's starting to say random things on the side there. So yeah, once the countdown is over, then it'll start processing what it's just heard.
Buckets, bags,
and then you can see it over here. There's a 5-second cooldown to just indicate that it's done. And yeah, now it's doing the processing. Countdown, tell you how much time you have left, and you can see all the processing here.
Hi Larry, I'm currently trying to get the system working.
So, here's the full output file from the recording we just did. You can see that it did a decent job captioning some of the stuff that I said earlier. It didn't do as well in captioning Charlie, though, due to the noise in the background, as well as Charlie's stronger accent. The talking in the background makes this a pretty good stress test, however.
Allow me to explain how our final solution approach works. First, we use the camera to identify the location of each of the speakers. To do so, we apply pre-trained Detectron 2 image segmentation. Next, we apply state-of-the-art speech separation technique SEP format to separate the overlapping speeches. We then transcribe each of the separated speech using state-of-the-art speech-to-text models from IBM Watson. To assign the transcribed speech of each speaker to the speaker who spoke it, we apply signal processing techniques such as beamforming. As two people are having a conversation, the speech of one of the speaker will always reach one of the microphones earlier than the speech from the other speaker. Therefore, we can use cross-correlation of the separated speech from each of the microphones to determine if the time delay is positive or negative. If the time delay is positive, we assign the transcribed speech to the left speaker and right speaker if the time delay is negative. Finally, we overlay the transcribed captions to each of the speakers. Once the video output is ready, the website will refresh and the transcribed video is displayed on our website. This system diagram summarizes our 5-steps approach that I mentioned earlier. We tested our experiments in a conference room on the 4th floor of the Collaboration Innovative Center at Carnegie Mellon University with a controlled setup as shown here. We chose this location as it is similar to the Danforth lounge location where we will be carrying out our final demonstrations. At this location, we were able to create our complete dataset that we will present during our final report. We marked out the angles of each of the speakers for consistency purposes. Here, we demonstrate an example of our auto-captioning system on our very own American English-speaking members, Larry and Stella, in a much quieter environment.
Most computers are digital, which means that they represent information using binary digits or bits.
Most computers
come in different shapes and sizes.
As you can see here, our auto-captioning speech separation system is able to perform much better. This is expected as our system is designed primarily for the American-speaking audience.
Now, here's a recap of our use case requirements along with our testing methods. So, starting with minimum number of speakers. Our system currently only works with 2 speakers, but in the future it could be adapted to work with more. For the quality of video played, as I said before, we checked our camera specs, confirmed that we get the desired video quality. We did aim to get our total processing time down to less than 3 minutes, which we do achieve. And this processing time is measured from when we stop recording to when the captioned video is ready for the users. Now, the part that took the bulk of our testing was this first metric, the accuracy of the speech-to-text output. To test this, we followed the diagram that you see here. Raw speech is the speech before any audio processing, so if there are 2 people speaking, you'll hear both of them clearly. And separated speech is after speech separation, so if there were 2 people speaking in the raw audio, separated speech will only ideally have one of them. Then we pass each of these through our speech-to-text model and get transcripts for each of them. And then we compare those transcripts to the original script, which the speakers would have been reading off of when we recorded these. And that way we get word error rate. Now we have these 2 word error rates. The word error rate of the separated speech is what we really want. That tells us how well our system is performing on the separated speech, which is what it will actually use. The raw speech gives us a good baseline to compare separated speech to, because this is how the system would perform if we did not perform speech separation at all.
We tested our system across a more robust dataset. First, we compared the word error rate of just one speaker speaking as the baseline. Next, we tested scenarios where one of the speakers interrupt. We also tested partially overlapping speeches as well as fully overlapped speeches. Our results demonstrated that our speech separation technique achieved lower than 20% word error rate for most of the scenarios, meeting Microsoft Audible comprehension benchmark. This indicates that our speech separation system is robust to most types of interruptions and overlapping speeches.
One of the big things we changed over the course of our project was that we started out with an array of 6 microphones. And now, instead of using 6 microphones, we're only using 2, so a stereo recording system. The reason we were using 6 initially is because we were planning on using beamforming to separate speech, but afterwards we found that beamforming did not work nearly as well as deep learning, so we switched over to deep learning, which technically only requires 1 mic. EyeHear is a useful product for captioning any unscripted visual audio experience. For example, one could caption an improv show where the back and forth dialogue between actors is important to keep up with. EyeHear could also be used to record and caption a discussion or a meeting where the speakers wish to make the content more accessible, but don't have the time to set up individual mics for everyone or to caption each speaker by hand.